Hello friends. So today we are going to discuss the questions from the modern physics, and we are going to solve questions from the year 1981. There are a total 2 questions. From 1982 we are having 1 questions. 1983 we are going to solve 3 questions, and from the year 1994 it is our 1 questions. So in totality we are going to solve 7 questions. And all these 7 questions are from the modern physics. So the first question, it was asked from the year 1981, and it states that the half life of the radioactive radon is 3.8 days, the time at the end of which 1/20th of the radon sample will remain undecayed is given as log of 10 to the base e. The value is given, it should be log of e to the base 10. So it has to be log to the base 10 and value is our e. So in this case we are given that half-life of radioactivity is given. So we are given that half-life of radon, we can easily call it as T half, and that is given as 3.8 days. And we are also given that only the 1/20th of the sample should be remaining. So basically we are given the final fraction which should be remaining. So you can say final fraction remaining that is should be our 120, and which basically means that the ratio of our NT upon N naught should be equal to 1/20. Okay, and we need to find out this value of T. Okay. So we already know the standard formula for NT upon N naught, that is also called as exponential decay law. Which gives us NT upon N naught is equal to e raised to power minus lambda t. And we are going to take natural log for both sides, and NT upon N naught is given to us as 1/20. So let me substitute it. So this is our 1/20 is equal to e raised to power minus lambda t. So if we take natural log of both sides, we get natural log of 1/20 will be equal to minus lambda by t. And we can write this as minus of log natural log of 20 is equal to minus lambda time t. And this minus and minus goes away. So from here we get that our lambda t is equal to natural log of 20, and we are required to find out this value of lambda, which is also our decay constant. So we can say that decay constant, which is our lambda, is given as natural log of 2 divided by t half, and we substitute the value, which we get as 0.693, t half is our 3.8. So from here we get our lambda. Okay, we can just substitute our directly. Therefore we can say our t will be equal to natural log of 20 divided by lambda. We substitute value of lambda, and this comes as natural log of 20, 0.693 multiplied by 3.8, and this comes as approximately as 16.42 days. So option number B is correct. Is correct. Next question. It was asked in the year 1991, and it states that a single electron orbits around a stationary nucleus of charge plus Z multiplied by E, where Z is a constant and E is the magnitude of the electronic charge. It requires 47.2 electron volt to excite the electron from the second Bohr orbit to the third Bohr orbit. The ionization energy of the hydrogen atom is, this should be actually 13.6 electron volt. Bohr radius is 5.3 into 10 to the power minus 11 meter. Velocity of light is 3 into 10 to the power 8 meter per second, and Planck's constant is 6.6 into 10 to the power minus 34 joules second. So based on this, we are having these 5 questions. First one is we are supposed to find out value of Z. Okay. And we are given that the electron will be excited from the second Bohr orbit to the third Bohr orbit, and so energy required is 47.2. Okay. So we can say that our value of n is 2, and the excited level is value of n is our 3. So based on this, we can write that our E3 minus E2 will be equal to 47.2 electron volt. And we need to find out first of all the value of Z. And so is our part A. And we know that our, in like you can say hydrogen like atom, we can write when the nuclear charge is given as Z multiplied by E. So we can say that in hydrogen like atom, for a nuclear charge plus ZE, we can write the equation for the energy for the nth orbit. We can write that our E of n will be equal to minus 13.6 Z square divided by n square, and this is our electron volt. And value of n we already know is 2 as well as 3. So therefore we can write this particular equation for respectively value of n is 2 and when value of n is 3. So we can write that our value of second orbit, the energy of the second orbit, will be minus 13.6 Z square, and this comes as our 2 square electron volt, and this will be coming as minus, this will be our 4, and it will be coming as minus 3.4 Z square electron volt. Similarly, we can write for our value of n, that is our third orbit, this will be our 13.6 Z square, and we have this as 3 square electron volt, which will be coming as our minus 1.51 Z square electron volt. And the difference between the two, that is our E2 minus E3, E3 minus E2 is already given to us. So we simply subtract these two. We can write that our E3 minus E2 will be equal to, we have our minus 1.51 Z square, and minus of E2 is minus 3.4 Z square, and this will be coming as our minus minus plus, so this will be 1.88 Z square. But the difference between the energy is given to us as 47.2, will be equal to 1.88 Z square. So from here we can get directly the value of Z will be, Z square will be close to 25, which gives us that value of Z is equal to 5. So this was our part A. Now we come to the part B. Part B states that energy required to excite the electron from the third to fourth orbit. Okay. And here we already got the value of Z, so we can easily find out our E3 as well as E4. And the energy required, will be the difference between the two. And the formula which we are going to use is the energy for the nth orbit. And so we can say that our E of 3 will be minus 13.6, and Z is our 5, so this comes as multiply by 25, and this is our 3 square, that is our 9, which will be coming as minus 37.78 electron volt. And similarly we can find out for the fourth one, this will be also minus 30.6, and value of Z will be our same, value of N will be our 4, which comes as 16, giving us minus 21.25 electron volt. Now we require to find out the difference, that is E4 minus E3 will be equal to minus 21.25 minus of minus 37.78. This gives us 16.53 electron volt. So this was our part B. And part C states that wavelength of EM radiation required to remove the electron from the first orbit to the infinity. Okay. So we have to move from the first to the infinity. So we can just use our basic equation that E is equal to hc upon lambda, and we require to find out our E, and that is from 1 to infinity. Okay. And so we easily find out E1, and for E infinity, value of n is infinity, so it is automatically equal to 0. So we are only interested in our E1. So our part C, it states that value of n is 1 to value of n is infinity. So we can find out value of E1. E1 will be equal to minus of 13.6, and Z is our 5, so this comes as 25. Value of n is our 1, and this gives us minus 340 electron volt. And we are going to convert this into our joules. So simply we are going to multiply it by 340 into 1.6 into 10 to the power minus 19, and this gives us that our E1 will be equal to 5.44 into 10 to the power minus 17 joules. Now we are going to use the relationship between the energy and wavelength. Relation between energy and wavelength. And we know that E is equal to hc upon lambda. So which gives us, because we are supposed to find out wavelength, so this gives lambda is equal to hc upon E. E we just found out is for our first, that is our E1. So let me write E1, which gives us 6.6 into 10 to the power minus 34. Speed of light is 3 into 10 to the power 8, and E1 we found out is 5.44 into 10 to the power minus 17. So we get our lambda is approximately equal to 3.64 nanometers. And part D, we are supposed to find out the kinetic energy, potential energy, and angular momentum in the first Bohr orbit, and the last is the radius of the first orbit. Okay, so it is directly you can say based on the formulas, all these parts. So we write for part D. First is our we just calculated our energy E. So let me, energy E was our minus 13.6 Z square, and it is for first Bohr orbit. Value of n is equal to 1, so it comes as divided by 1, which we get as minus 340 electron volt. And our kinetic energy is our negative of the energy we just calculated, so it comes as 340 electron volt. Our potential energy will be equal to 2 times E, so this comes as minus 680 electron volt. And we need to find out the angular momentum, which is our L, that is n multiplied by h, value of n is over 1, value of h is a standard which is 1. Value of h is 1.00055. This is, 1 second, I think, this is not our Planck's constant, but it is written as n multiplied by value of, you can call this as, I think, h prime or something it is called. I'm not able to recall it now. And this comes as 1.055 into 10 to the power minus 34 joules. And finally, we are going to find out the radius, that is our part E, a radius of first Bohr orbit. Radius of first Bohr orbit. For nth, we know the formula that our R of n is equal to n square a naught upon z. So therefore, we can write our R1 will be equal to 1 whole square a naught by z, and a naught is our 5.3 into 10 to the power minus 11, z is our 5. So we get our R of 1 will be equal to 1.06 into 10 to the power minus 11 meters. Next question. It was asked in the year 1982, and it states that hydrogen atom in its ground state is excited by a means of monochromatic radiation of wavelength 975 angstrom. How many different lines are possible in the resulting spectrum? Calculate the longest wavelength amongst them. You may assume the ionization energy of the hydrogen atom is 13.6 electron volt. So here we are given two things. One is given an ionization energy, and another one we are given as a lambda. And we are supposed to find out our value of different line possible, which is our value of our n. Okay. And in order to find out the value of n, we should be knowing the energy, because we are going to use the energy equation for the nth orbit. So we can just easily find out our energy because wavelength is given to us. So we say that our energy of the incident photon, energy of the incident photon, using the relationship between the energy and wavelength, we get our E is equal to hc upon lambda, and this comes as 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8, and lambda is our 975 into 10 to the power minus 10. This comes as 2.037 into 10 to the power minus 18 joules. So we are going to convert into electron volt. So we get our E is equal to 2.037 into 10 to the power minus 18, 1.6 into 10 to the power minus 19. This comes as 12.73 electron volt. Now we are going to use the energy level equation, that is for the nth one. So you can say that highest energy level excited, highest energy level excited, and for that obviously means we have to find out value of n. So therefore we can write that our E of n is equal to minus 13.6 into 1 upon n square electron volt. And we have to find out that our maximum level of n from the ground state. So you can say that maximum level n that can reach, that can be reached, that can be reached from the ground state it is given as E of n is equal to minus 13.6 plus 12.73, and from here we get our E of n is equal to minus 0.87 electron volt, and E of n is also governed by the standard equation, which is equal to minus 13.6 into 1 upon n square. So here minus and minus cancels out, so we get our n square will be equal to 13.6 divided by 0.87, and this comes approximately as 15.63, which gives us the value of n is approximately equal to 4. So the electron excites from n to 4, from n is equal to 1 to n is equal to 4. Okay. And we have to find out the number of spectral lines that will be emitted. We got already the value of n, so it is quite straightforward now. So we can write number of spectral lines will be equal to n minus 1 divided by 2. So this gets a 4 multiplied by 3 divided by 2, and this 4 goes by 2, which gives us 6 lines. And we can approximately draw the levels also, because we have value of n is from 1 to 4, so therefore we can say that this is value of n is equal to 4. Next will be our value of n is equal to 3. Next we can draw our value of n is equal to 2. and finally we have n is equal to 1. And the spectral lines are 6. So first of all we can say that from 4 to 1, then we can say 4 to 2, and then we can say 4 to 3, and then we can say our 3 to 1, and finally we can write our 3 to 2, and the last one is from 2 to 1. So all these are 6. This is 1, 2, 3, 4, 5 and 6. And for the longest wavelength, the energy difference should be minimum. And you can say for longest wavelength, the energy difference should be minimum. And this is also true from the energy wavelength equation, because energy is inversely proportional to wavelength. And this is for when there is a transition from 4 to 3. Under this condition, however, it will be minimum. And we can use our value of n. We already know is, let me write it, value of n is our 4, and it goes value of n is equal to our 3. We can use the Radioactive formula. So we can say from Radioactive formula, we have 1 upon lambda is equal to RH, that is a constant, 1 upon n1 square minus 1 upon n2 square. So we already know, we substitute it and we get our 1 upon lambda is equal to 1.097 into 10 to the power 7, and we get this as 1 upon 3 square minus 1 upon 4 square. And from here we can say our value of lambda is close to 1875 angstrom. Yes, so this is, question is complete. We come to the next question. It was asked in the year 1983, and it states that ultraviolet light of wavelength 800 angstrom and 700 angstrom, when allowed to fall on a hydrogen atoms in their ground state, is found to liberate electrons with a kinetic energy 1.8 electron volt and 4 electron volt respectively. Find the value of the Planck's constant. So here we are given two wavelengths, and corresponding to that the kinetic energy of the electrons that are emitted is also given. So let us say that first wavelength is our lambda 1, which is our 800 into 10 to the power minus 8 meter, and corresponding to it the kinetic energy is our 1.8 electron volt. And we have a second wavelength, that is our lambda 2, which is given as to us as 700 into 10 to the power minus 8 meter, and the corresponding kinetic energy is given to us as 4 electron volt. We are supposed to find out our, you can say, Planck's constant. Okay. So we are going to start with the photoelectric equation, which gives us relationship between the kinetic energy, wavelength, as well as the work function. And in this case, the material is same, and so work function will be same. Okay. So we can write that our photoelectric equation which gives us that kinetic energy K H is equal to hc upon lambda minus phi. And we have two cases, so we can divide this equation into two parts. K1 is equal to our hc lambda 1 minus phi, and we have second one, that is our K2 hc lambda 2 minus phi. Simply subtract them, phi and phi are going to cancel out. We get this as K2 minus K1 is equal to SHC, and we have 1 upon lambda 2 minus 1 upon lambda 1. And we already know K2 and K1 are given to us, so we substitute them. K2 was our 4 minus 1.8, and this is electron volt, so this comes as 1.6 into 10 to the power minus 19. H we are supposed to find out, and speed of light is 3 into 10 to the power 8, and we already know that our lambda 2 is 7 into 10 to the power minus 8 minus 1 upon 8 into 10 to the power minus 8. So from the left side, this will be equal to 3.52 into 10 to the power minus 19 is equal to H 3 into 10 to the power 8, and their subtraction will be coming close to as 1.786 into 10 to the power 6. So we get here our Planck's constant H will be equal to 3.52 into 10 to the power minus 19, 3 into 10 to the power 8 multiplied by 1.78 into 10 to the power 6. So this approximately equal to 6.57 10 to the power minus 34 joules, which is close to our the actual value of the, you can say, Planck's constant. Next question. It was also asked in the year 1983, and it states that to produce characteristic X-rays using tungsten target in an X-ray generator, the accelerating voltage should be greater than dash volts, and the energy of the characteristic radiation is dash electron volt. The binding energy of the innermost electron in the tungsten is 40 kilo electron volt. So here we are given the binding energy of the electron. And first of all, we are supposed to find out the accelerating voltage. So the minimum accelerating voltage should be greater than the binding energy. We are supposed to find out the accelerating voltage greater than. So we can say our that minimum accelerating voltage, if that is given as V, then this V should be greater than our, that is our 40 kilo electron volt. So this was quite straightforward, and similarly we are find out the energy of the characteristic radiation, and for that we require energy of characteristic equation. Energy of characteristic equation, sorry, not equation but radiation. And so for tungsten, the binding energy of innermost is given as is 40 kilo electron volt. So we can say that for K shell, binding energy that is our 40 kilo electron volt, and for L shell the binding energy is our 10 kilo electron volt. So therefore we can say that our energy for our X-ray, which we also call as a characteristic radiation, will be equal to energy for K minus energy for L shell, giving us 40 minus 10 is equal to 30 kilo electron volt. Next question. It was asked in the year 1993, and it states that the radioactive decay rates of the radioactive element is found to be 10⁻³ disintegration per second at a certain time. If the half-life of the element is 1 second, the decay rate after 1 second is dash and after 3 seconds is dash. So we are given that initial decay rate is given to us at 10⁻³ and the half-life is given as a 1 second. So we can start from there only. We are given initial decay rate that is our R0. It is given as 10⁻³ and we are given half-life which is our T half, and that is our 1 second. And we already know the equation for the radioactive decay. Okay. So we can say a radioactive decay that is for a time T is equal to our R0, and we have this as our half raised to power T upon T half. And first of all we are going to find out after 1 second. So we can say after 1 second or which basically means that value of t is equal to our 1, we get r of 1 is equal to r naught is our 10 to the power 3, and this comes as half 1 upon t half is also given as 1, so this 1 upon 1 is equal to, this comes as 500 disintegration per second. Then we are going to find out after 3 seconds. After 3 seconds, which means our value of now t is our 3, therefore we can write that our r of 3, initial r naught is our same 10 to the power 3 multiplied by half, and this comes as our 3 divided by 1 because half-life is 1, and this comes as 10 to the power 3 into 1 by 8, which gives us 125 disintegration per second. Next question. It was asked in the year 1994, and it states that the ionization energy of the hydrogen-like Bohr atom is 4 Rydberg. Based on this, we are going to solve these 2 questions. First is, what is the wavelength of radiation emitted when the electron jump from first excited state to the ground state? And then we are going to find out the radius of the first orbit for this atom. And the ionization energy is given as 4 Rydberg. We are going to convert into electron volt. And we know that 1 Rydberg is equal to 13.6 electron volt. So therefore 4 Rydberg will be equal to 13.6 multiplied by 4, which gives us 54.4 electron volt. And we already know the formula for our nth Bohr energy level. So first of all, we are going to find out the wavelength. So our part A, we know that the ionization energy which basically means energy required to remove electron from n is equal to 1. Ionization energy, which means energy required to remove electron from n equal to 1. So we get, because standard formula we already know, that our E of n is equal to minus 13.6 into z square and divided by n square. So value of n is 1. So we get this as E of 1 will be equal to minus 13.6 into z square, and E of 1 is already given to us, that is our 54.4. So this will be equal to minus 54.4. Therefore we get the value of z square will be our minus and minus cancel out. This comes as 54.4, 13.6, which comes as our 4, giving us value of Z is equal to 2. Now we can just find out our, we got the value of Z is equal to 2, which, because it is given that it is basically hydrogen-like atom, so therefore Z is equal to 2 tells us we are dealing with He1 positive ion. And ground state is our E1. Ground state E1 is equal to minus 13.6 into Z square, which will be obviously 54.4 electron volt. And first excited state, which is our value of N is equal to 2. This gives us E of 2 is equal to minus 13.6 into Z square divided by 2 square. So we get our E of 2 will be equal to 40.8 electron volt. And now we can easily find out our wavelength, and we get that our wavelength lambda is equal to our Hc upon delta E. Delta E is our difference between E2 and E1. So we can say our delta E is equal to E2 minus E1. E2 is our, E2 is our Z was our 2. So E2 is our minus 13.6 electron volt. So this comes as minus 13.6, and we have minus of E1 is 54 minus 54.4, and this will be coming as 40.8 electron volt. So this gives us H is 6.6, 5.6, 1 second. .6 into 10 to the power minus 34. Or we can just use product of Hc in terms of electron volt, that will be equal to 12.40 electron volt. We can just use directly also. 40 electron volt, and here we have 40.8 electron volt, which comes approximately equal to 30.39 nanometer. Okay, and remember this is itself in nanometer. Now we are going to find the radius of first orbit. Radius of first orbit we are going to use for the nth orbit. R of n is equal to our n square a naught upon z. value of n is 1, so we get our r of 1 is equal to 1 square. A naught is about 5.3 into 10 to the power minus 11. Value of z is about 2. So this gives us that our radius of first one is 2.65 into 10 to the power minus 11 meters. So this completes our questions from the year 1981, 82, 83 and 84. And the total question were 7 questions. This completes all the 7 questions. Thank you.